Today we're going to continue our discussion, kind of finish it on the quantum harmonic oscillator, which we in previous videos have showed that the spectrum or the energy levels are h bar omega n plus 1/2. And we've also looked at the energy eigenstates and derived what those are. And we indicate them just with some ket with an n corresponding to whatever eigenvalue, energy eigenvalue we're looking at. Now, today we're going to build on everything we've done with the harmonic oscillator and just sort of revisit time evolution and the time dependence of a state or some quantum harmonic oscillator system. So first, I want us to recall how we deal with time dependence. All right. Well, we have a Hamiltonian that's constant in time, right? There's no time dependence to it. So if you recall, when we're looking at time independent Hamiltonians, we have a nice little recipe of how to derive the state of the system as a function of time. And it all comes from the Schrodinger's equation, right? Which is the derivative of our state function, the time derivative of our state function times IH bar is goes as the Hamiltonian acting on that time dependent state function, right? This is Schrodinger's equation. It's how we determine the time evolution of pretty much of any system in quantum mechanics. But since we have the eigenstates, the energy eigenstates of our system, we can write this time-dependent wave function in terms of those. So this Schrodinger's equation, can just be written as the sum of uh, the linear combinations of our basis vectors, right? And we end up with something like this. Right? And all we've done is taken our wave function and written it as a linear combination of our basis vectors, which we can do. And these are time dependent. But since our Hamiltonian is time independent, our eigenbases of that Hamiltonian are going to be time independent as well. When we do this, well, the only thing with time dependence in here is our coefficients of that linear combination. And since these coefficients are just sort of scalars, they can come outside. This ends up being written, can be written as Cn, the operator acting on our, our energy eigenbases. Since these are eigenfunctions of our Hamiltonian, this side of our equation ends up being those Cn times the energy eigenvalues times n. This derivative, again, it's 0 for everything except for those coefficients. So we get this differential equation for our time-dependent coefficients, and it ends up, the solution to that, if you recall from last semester, was essentially the coefficient at the initial condition at t equals 0 times e to the negative I E N T over H bar. You can go through this. It's covered in 302, so I'm not going to go through all the gory details of that. But hopefully you remember this. This sort of mapped out how we solve for the time dependent of the time dependence of a system with a time independent Hamiltonian. The first step was just to determine what the energy eigenvalues are and those energy eigenstates are, right? And for the harmonic oscillator, we have e to the nth energy eigenvalue is just h bar omega n plus 1/2. And our energy eigenstates are just those n states, right? The second step was, well, take our state function at t equals 0 and cast it in terms of those energy eigenfunctions, right? So this is Cn at t equals 0 times En. And again, in our simple harmonic oscillator, this means take psi of t equals 0 and write it as a linear combination of those energy eigenfunctions, right? And we also know just that those Cn at zeros is just the projection of our state wave function at t equals 0 onto those energy eigenbases. The third step, the kind of the final one, is now we just add those phase factors that have the time dependence, these phase factors here. So our state function as a function of time now becomes the Cn's at t equals 0 plus these I to the En t over h bar um, terms there, those phase terms. So in our harmonic oscillator case, that ends up being our time-dependent state function is just the sum over Cn's at 0, e to the I. Our energy is h bar omega n plus 1/2 times t all over h bar times n, which can be simplified a little uh, and written as n Cn 0 e to the I omega n plus 1/2 t times n. If we like, we can actually factor out, every term here has an e to the I omega t over 2. So we can factor that out, e to the negative I omega t over 2, side of the n, there sum over n Cn 0 e, oops, that's negative, negative I omega n t times n, where we have this global phase that we're allowed to drop because, as we know, global phases, don't really have any physical meaning. Multiply any state by some global phase factor, you get the exact same physical state. So we've essentially walked through this recipe, and now we have our time-dependent state function here, and we can use that to calculate whatever we want for our harmonic oscillator at a later time using, the same way we use expectation values, are just, we would just use that with our time-dependent wave function in there. Probabilities of some measurement, we'll say A is just going to be the projection onto the state that represents that measurement outcome times our time-dependent state function squared. So we can do all of these things and figure out whatever we want. So let's do a quick example of that. For first example, let's look at, let's say, sorry about that. Let's say we have some harmonic oscillator that's in the state 1 over root 2, 0 plus 1 at t equals 0, right? So that's our t equals 0 state of our system. And we want to know, let's say, what is the probability of measuring this system in the ground state at some later time t, right? So the question is, what is the probability of measuring E0 at some time t? Well, first thing we have to do, like we said, is we already know our energy eigenvalues, as we just mentioned, and our energy eigenstates. So all we have to, the first thing we have to do is sort of after that is cast this in terms of these energy eigenstates, which, it was given in terms of the energy eigenstates. So we've already got 2 done as well, that this is our psi of t equals 0, right? So the third thing, add the phase factors, right? So our time-dependent wave function is going to be, right, the sum for n times Cn at t equals 0, e to the negative I En t over h bar times those n's, like we said above. In this case, the Cn's, well, we have C0 is 1 over root 2 and C1 is 1 over root 2. Everything else is 0. So this is e to the negative I omega, whoops, sorry. really sloppy. E to the negative I, this is the energy would just be h bar omega over 2. So this is omega over 2 times t, 0 root 2, plus e to the negative I, e to the negative I omega 1 plus 1 half t over root 2 times that state vector, and doing what we did above and factoring out that global phase, that's going to be equal to e to the negative I omega t over 2 times 0 over root 2 plus e to the negative I omega t times 1 over root 2. Right? So this gives us our state function as a function of time. We can actually just, if we like, drop that global phase, set it equal to 1, because we have the freedom to kind of choose any global phase we want. So now we can actually look at the question of what's the probability of measuring E, E in the energy in the ground state at some later time. And we just use postulate 4 from the textbook, which is, well, if we measure the 0th state, we're projecting onto that ground state energy of psi of t all squared. So we can quickly do this in sort of Brockett notation. We have 0 inner product with 0 over root 2 plus e to the negative I omega t 1 over root 2, just plugging in what our time-dependent state function is. The 0 inner product with itself is 1, so that ends up being 1 over root 2 there. And since 0 and 1 are orthogonal, that's the 0 squared. So that probability is 1/2, right? And it's constant, it's independent of time. We should have probably expected that. It is an energy state. The probability of measuring, of any measurement of energy will be time independent for a time independent Hamiltonian, right? If you think about that, that kind of makes sense. The Hamiltonian is the energy operator. That shouldn't really, the energy shouldn't change as a function of time unless you do some sort of work on the system. So what about something else? What if we look at the probability distribution as a function of time, right? So this is essentially how does the wave function as a function, the wave function evolve as a function of time? Well, to do this, remember that wave function is essentially just the projection of our state function as a function of time onto the position bases. So we can write that this way, right? Down to x. And we just derived our time-dependent state function as this, I omega t over root 2, 1. And if we just carry out, knowing our Dirac notation, and that this ends up being x 0 over root 2 plus e to the I omega t over root 2 x on 1. These sort of terms here are just our energy eigenfunctions, right? So this whole thing ends up being the n equals 0 wave function over root 2 plus the n equals 1 wave function times e to the negative I omega t over root 2. This all squared, right? So we can factor out the 1 over root 2, square it, and bring it out front. This ends up being 1 over root 2 times, if I want to take this sort of magnitude squared, I'm just going to take the complex conjugate and multiply it with itself. So we end up with phi 0 complex conjugate plus phi 1 complex conjugate e to the I omega t, and multiplied with phi 0 of x plus phi 1 x e to the minus I omega t. Right. This doesn't need to be here anymore. So just again, carrying through some really riveting math here, this ends up being just phi 0 of x squared, the magnitude of that squared. Now, yeah, I'll let me write this out in full. I'll add a little more detail here. So the complex conjugate times phi 0 of x plus same thing for 1, right? That's this term and this term plus this term times this term. But now we have the cross terms, right? So we have phi 1 of x, phi 0 of x e to the I omega t plus phi 0 of x, complex conjugate of that, phi 1 of x e to the minus I omega t. And we have those cross terms. Now, because we know the eigenfunctions of our harmonic oscillator are real, this can just be written out as phi 0 squared. I'm going to get rid of explicitly writing that they're a function of position. Hopefully we can remember that. Phi 1 squared plus, we can factor out, since these are real, that, and we have phi 0, phi 1 times e to the I omega t plus e to the minus I omega t. Or simplifying this and using just our cosine, that's going to look something like this. It's going to be this, cosine omega t. Right, so we do have this time dependence in here. I've used the identity cos x is equal to e to the ix plus e to the minus ix over 2. Hopefully we all remember that. But the point is, our probability density as a function of position and time does have this time dependence here, which sort of makes sense. Last video we showed that the Hamiltonian does not commute with the position operator, so we might expect this. That basically the probability distribution is going to slosh back and forth in that harmonic oscillator, right? So what else can we look at? Let's look at, say, the expectation value of the position as a function of time, right? Now, we know that this is equal to just the bra times the x operator on the ket. So we can do this, and we could, one of the ways we've done this in the past is just put this in the position representation, integrating over all space, the complex conjugate of our wave function as a function of time, times the x operator in position space, times the wave function as a function of, well, position and time, integrated all over all space. These wave functions are multiple or linear combinations of all the energy eigen wave functions, and this can take a lot of work, a bunch of integrals, but we can actually simplify our lives a bunch again using the operators, the raising and lowering operators, rather than this sort of brute force integration, right? So if we recall, the x operator can be written as h bar over 2m omega all square rooted times the raising operator plus the lowering operator, right? So this means that we can write our expectation value for position as a function of time as psi of t with that operator inside, h bar 2m omega, a dagger plus a psi of t, right? And we previously showed, what these the time dependent state functions were, so we can write this as what we got in that situation, e to the I negative I omega t over root 2 because we're taking, again, recall the complex conjugates when we move to the bra. H bar over 2m omega square rooted a dagger plus a times the state ket as a function of time that we derived above. When we do this, we know how these raising and lowering operators act on our energy eigenkets. Remember, the raising operator acting on n just equals root n plus 1 times the the ket 1 up in the ladder of energy states, and the lowering operator is just root n times n, right? So we can sort of really quickly see how this is going to act on our state ket. Sorry, really need to cut and paste with my tablet here. So this raising operator acting on the 0th state gives us root 1 times the 1 state. So this is just 1 over root 2. It acting on this term gives us, root 2 times e to the negative I omega t over root 2 times the second ket. This lowering operator acting on these gives us, well, the lowering operator acting on the ground state, that's our ladder termination condition, so that's just 0. And acting on the 1 state gives us root 1 times the 0th ket, so we have e to the negative I omega t 0 over root 2, right? And now, because we know our energy eigenkets are orthonormal, this becomes really sort of straightforward to deal with, right? I'm going to bring this term out front, but let's look at that term times that term. Well, 0 and 1 eigenstates are orthogonal, so that's a 0. This term and this term, again, orthogonal, so that's 0. This term times 0 is 0. And the final one is the only non-zero term that involves this, and it just brings us e to the negative I omega t over 2, root 2 times root 2, and the 0 inner product with itself gives us, it's just 1. Now we can go to these terms, the 1 and this term are going to give us e to the, oops, this is supposed to be positive there. E to the minus I omega t over 2, 1 and 1. This term inner product with that, well, the 1 and 2 states are orthogonal, so that's 0. This one's 0, this one's 0. They're all orthogonal. So really quickly, we end up with the expectation value of position as a function of time is equal to 1/2 e to the I omega t plus e to the minus I omega t, which again, using our cosine identity, is just h bar over 2m omega all square rooted cosine omega t. Praise Newton. We figured this out without doing a single integral, just using our raising and lowering operators. And what we see is that superposition initial state is the expectation value for position is just going to slosh back and forth, right? And we know that expectation values, to the Ehrenfest theorem, expectation values follow classical principles, right? So if I wanted to know the expectation value of the momentum as a function of time, well, it's just mass times the derivative with respect to time of the expectation value of position as a function of time. And essentially we see this particle in the harmonic oscillator oscillating back and forth, much like we would expect for just a classic harmonic oscillator. Um, so again, the operator method, these raising and lowering operators can make our lives a lot easier in a lot of these calculations, but we've gotten to a point where we've looked at the harmonic oscillator for a while now. We can basically start to approach all sorts of different problems and answer a bunch of questions we'd want to. We're going to go through, discuss this more in our synchronous sessions. If you have questions, bring them up, email me. I will see you then.